So I'm going to jump forward here to 4.7, which is applications involving exponential functions. And the other chapters are important, and I'm going to backtrack to them, but they're mostly about using radicals and the accuracy of radicals and simplification and transformations. And you'll discover that all these functions follow the same transformation rules. But I want to look at an example here. And in this case, I've given you the graph, the formula, and the data. And we're going to look at various things, but one of the most difficult things before we learn how to use logs is if let's pretend this is just I don't know, growth of bacteria, and it's growing at 3 times the rate, and this is hours or whatever, every hour, and it starts at 10 bacteria. And you can usually see, it'll start at 7 bacteria, and you can usually see the start when x is 0. You can say, okay, it started with 7 bacteria, and every hour we can see how it goes by 20, it grows by 60, it grows by 180, and we could do the first differences where we subtract, and we'd quickly realize our first difference is 27 minus 7 is 20, 87 minus 27 is 60, and the next one is 180, and then we can do second differences, and we get 40 and 60, and we discover, oh, our first and second differences aren't leading anywhere, and that's instantly will tell us we're probably dealing with a growth curve. But in this case, I want to deal with a situation where they're going to give you the answer. In other words, they're going to give you y, and they're going to want you to figure out x. And until we're given logs and learn logs, you have to sort of guesstimate. And I'm going to show you how to guesstimate. So in this case, if they give it to you graphically, you would find y is equal to 21,867 on here, and you draw it, and you'd look at your graph and say, okay, well, my x is 7. And that's easy if we can draw it graphically. So that's one way to find it graphically. You find your y on this chart, and you follow it out, and you'll find your x. Great if we have the graph, but let's say we don't have the graph, and all they give us is the formula. So I'm going to start with that premise. And this is a really important skill, and most students have trouble with it. So let's say they want you to find when y is equal to this, and they give you the formula, which is essentially just y is equal to this. Okay. That's what they give you. They say find x when y is equal to that. Well, it's clear that what we do is we take this and we put it on the left side, and we take the rest of the equation, and we try to solve for x, but we haven't learned any tools yet to solve for x. So let's just try to get to x. Let's try to get to this part by getting rid of this stuff. So you have to unravel the equation the same way in bed mass order. In other words, what's happening to x? X is an exponent. Then that exponent is getting multiplied by 10. And then it's minus 3. Now, a lot of people have trouble with this part of it because they're trying too hard to get to x. But if you just for a second pretend, let's pretend that's something else, and we're going to replace this whole thing with just x. We're going to let x equal this whole thing, and it could be anything else. Let's say a. Okay, a. And if we were going to unravel, it's quite clear that a is being multiplied by 10, and 3 is being subtracted by it. So to reverse that, I don't divide by 10. I have to add 3 to both sides. And it's very clear how to get rid of a. And if I add 3 to both sides, I have to add it to the left side now. I get 21,870 is equal to 10a. And it's clear now I have to divide it by 10. 2187 is equal to a. And now I can bring this back. It's a lot easier to solve now. And I can do this now. Okay, now I know that 3 to the x is equal to that. Now, until you learn logs, I'm going to show you the sneaky future method, and I'm going to show you the basic here. Essentially, you have to figure out what number 3 to the power of will closely become 2187. Now, you can do it like this. You grab a calculator, okay, 3 to the 1, you put 3, you hit multiplies. So that's to the 1, and when I hit equals, that's to the 2, that's to the 3, that's to the 4, that's to the 5, that's to the 6, that's to the 7. Suddenly I quickly discover, oh, 3 to the 7 is equal to this. Therefore, x is equal to 7. And until you learn logs, that's the way to do it. Now, logs are like the the inverse of exponentials. Logs are like when we swap x and y in the equation and we're trying to figure out the inverse equation. So when I take the inverse of this, I can't right now until I learn logs. However, once we get to this stage, remember we were at this stage, 21, was it 870? Yeah, 87 is equal to 3 to the x. Well, you can do what's called taking a log of both sides, and just trust me, just go with it. I'm going to take a log of both sides. And the log rule, and actually I didn't even need the brackets there, so I'll kind of get rid of them. The log rule says that when I have an exponent here, I can just simply put it in front as a multiplier. That's a rule that you're going to learn in logs. Now to solve for x, I just have to, it's being multiplied. You might say, well, what is log 3? These are just numbers. I'm not going to get into what logs are just yet, but they're just numbers. So how do I get rid of a number that's multiplying x? I divide both sides by log 3. It's going to cancel out here, and then I have to put it on this other side. Okay, just play along. Log 3. Boom. So apparently x is equal to this number, log 2187 divided by log 3. Okay, well fortunately there's a log button on your calculator. 2187. Let's see if we can find the log button. There it is. All calculators have it, so I'm going to hit log, and then I'm going to divide it by 3 log equals. And boom, look at that. It gives me the answer of 7. So if you just want to learn this quickly on a test, that way you can verify that you got the right answer, you take a log of both sides. Once you get it down to this, you take a log of both sides, and the rule for logs is whatever exponent is up here can now come down in front. Like this. X times log 3. And then you just divide both sides by log 3. And you get that. So essentially, x is always going to be equal to the log of this divided by the log of its base. As long as there's no adjustments up here. If there's like a plus 1, we then have to subtract 1 to the other side, etc. So you might have to do extra algebra, but this is the tough algebra. Once you have this down pat, you'll be able to figure out. Now, I'm not going to go into too much about what logs are, but I'll show you the relationship to logs. And the reason I show this to you now, it's grade 12 stuff, but it'll help you verify answers because your teacher will expect you to guesstimate the way we just did. But essentially, here's the relationship. 2 to the power of 3 is clearly 8. And that's the same thing as saying, okay, well, log base 2 of 8 is equal to 3. And what this question over here asks is, what exponent do I have to put over 2 to get 8? So before we know this answer, what exponent do I have to put over 2 to get 8? To get the result of 8? And the answer is 3. Now, when in your calculator, logs are always base 10. In other words, let's do a 10. A 10 to the power of 4 is equal to a 1 with 4 zeros, or 10,000, which means log of 10,000, if I ask it like this, is equal to 4. And in your books, they're not going to write this with the 10, because if it doesn't show a number as a base, it's always base 10. But this question is asking, what exponent do I have to put over 4 to equal 10,000? Or sorry, what number do I have to put over 10 to get a result of 10,000? And the answer is 4. So that's the connection. They're just directly related. Students have a hard time sort of understanding this point, but it gets easier with time. Lots of things are measured by log, by the way, in science. pH is a log scale. Earthquakes are a log scale. Decibels, sound, are a log scale. Now let's just get back to the guesstimate technique, though. Suppose it wasn't so clean. Suppose it wasn't so clean. Suppose they wanted me now to find a y of, let's say, find when y is equal to 3,000. Okay? Well, it's the same technique. I have to do 3,000 is equal to this equation. Then if you have trouble understanding how to isolate, you can always let A equal to this. You're always allowed to substitute and resubstitute back in math. It's a very handy skill to learn. So let's call it A, 10 times A minus 3. I add 3 to both sides. I get 3003 is equal to 10A, and therefore 300.3 is equal to A, and then I just bring it back. I bring back my substitution. I bring back what A was standing in for, and A is standing in for that. So now I've got this, so I'll just erase everything else. But you can also see that if you're comfortable with it, you could have just left this alone, and you add 3 to both sides, and you divide by 10, and you end up with this is equal to that. But it's clear this is harder to see, right? So here's the problem is, okay, there's 3 to the power of 1. I hit the multiplier. That's the power 2. That's the power 3. That's the power 4. That's the power 5. And that's to the power 6. So let's go back. So this means this number is clearly between 243 and 769. I think it was. Was it 769 or 789? Let's just go. Times 3. 729. Clearly, when this number 303 falls between 3 to the power of 5 and 3 to the power of 6. 303 falls somewhere in there. Now, if I look at the span here, there's a 500 span roughly, and 300 point is much closer to 243. So if I look at this as a scan of 1 to 10 in here, and I divide each thing, so there's 500 different, so each 50 is 0.1. I could say 0.50 is 293, so it looks like it's going to be 5.1. And then 293, and it looks like that's going to be another like 0.5, something like that. And you can see that this guesstimation becomes a big pain in the butt. But let's see, how would I put that as an exponent to see if I'm close? Well, let's try 5.1. 3 to the exponent of 5.1. It's 271, so I'm too low. Let's try 3 to the exponent of 5.2. 302, very close. So really, it's something like 3 to the exponent of 5.199. Very close. Let's try 3, and you can see how this is a pain in the butt. 3.118. Let's try that. Too low. 3 to the exponent of 5.185. Still too low. So 3 to the exponent of 5.1905. So it has to be above 9. But you can see it's a pain in the butt. Let's try 1.592. Pretty close. So I can see that it's roughly x is equal to 5.1915 sort of thing. Hard. I'm only going to ever be able to guesstimate without a log technique. But let's look at the log technique. So I take a log of both sides. The rule of log says I can bring that x down in front as a multiplier. So it's x times this. To get x all alone, I'm going to divide both sides by log of 3. And it turns out I'm going to find my exact x value by taking the log of 300.3 and dividing it by, take a log, and dividing it by log 3. And I might have hit too many buttons there. Yeah, I hit too many buttons. So let's try it again. 300.3 log divided by log 3 equals 5.1927. So here I had 5.19205 or whatever. But here I've got x is equal to a very clear exact number. So I can see how close I was. Guesstimation when with exponents, when it's not clean, when it's between two numbers, becomes very difficult. But becomes very easy. Now let's go back to the first thing. This is another important skill. So let's say, great if we could check on the graph. And let's go back and check, we can set this to any y I'm interested to. And when I zoom in on the graph, I'm going to find my x value. So 3.59 will yield a y of 500. So it's very useful if I have a graph. I can just set my y to whatever. Let's say y is equal to 1200. Then I find where it crosses, and that's going to be my x value. So it's very easy when I have a graph calculator or Desmos at my fingertips. Now in university you do, and even in high school you're allowed to use a graphing calculator, but probably not for a test. Now let's go back to just the data. Clearly I can see a formula, and clearly there's no x transformations because there's nothing affecting the x up here. The base is 3, but there's two y transformations. There's a vertical stretch of a factor of 10, and then there's a vertical translation down by 3 units. But if I couldn't see that, and I knew I was did first differences, and I knew I was dealing with an exponential, the secret is to go up to these top numbers to figure out the base. So I'm going to take 21867, and I'm going to divide it by the number before it. This only works when the x's go up by 1, by the way. You have to make sure your x's go up consistently. And I can see that my base is probably 3, but I'm going to take the number before it, and I'm going to divide it by 2427 and see if I get 3. And yeah, I can see with those bigger numbers that it's quite clear that it's going to be, it looks like the base is 3. The reason I use the big numbers is because that way the 10 multiplier and the 3 subtraction don't have as big an impact as the exponential growth base number. These become insignificant. Whereas when I look at it down here, 27 divided by 7 is roughly 3.5, right? I'm not getting a good base there. But as I go up, and this one here is like 3.2. But as I go up, I can see it gets closer and closer and closer to 3. So I can right away say, well, I think it's 3. And this also tells me something. If it's 3 to the power of 0, which is when x is 0, and it's either adding and multiplying something, an a and a b, and it's equaling 7, well, that could mean that there's no a and the b is just 7. And I can always try that out. What's 3 to the 1? It's 3 plus 7 should be 10. But I can see, oh, it's not 10. It's much higher than 10. So I'm quite sure it's not just adding 7 right away. So I kind of know that there's more of stretching going on just from that. But I can take a very basic formula and say, okay, I suspect it's base 3, and it's going to be a times base 3 to the power of x plus a mysterious b, and it's always going to equal to y. And then I can go one by one with the numbers I take. Okay, well, when x is 0, I get a times 3 to the power of 0 plus b. And what is my y when x is 0? 7. Okay, I know 3 to the 0 is 1. So I know that a plus b is equal to 7. Or a is equal to 7 minus b. Well, that's what I got from the first number. Now I'm going to go and work with x is 1. Well, when x is 1, y is 27. Okay. Well, 3 to the 1 is 3, so I get 3a plus b is equal to 27. But in the first equation, I discovered that a is also equal to 7 minus b, so I can replace it like that. Suddenly I have all b's. 21 minus 3b plus b is equal to 27. When I subtract 21 from both sides, I get, and what's minus 3b plus b? Minus 2b is equal to 6. Oh, look at that. b is equal to minus 3. And if I go back and put it into this equation, a, what's 7 minus minus 3? A is equal to 10. Suddenly, I was able to figure out A and B from that information. So suddenly I've got a 10 times 3 to the x minus 3 is equal to y. Now, there were no x transformations on this, and that makes a difference because the x transformations will indeed make this difficult. However, at this stage, when you're asked to deduce these things, you're usually only working with y transformations. We'll get more into x transformations later. But you can see that these are useful techniques for solving any equation, knowing first differences, when something doesn't have first differences in a ratio, and how to solve it. And that's without logs. But I'm teaching you the logs because it's kind of a jump up on next year, but also it can only help you in verifying your answers. So here we're talking about the growth of a population since 1996, which we would call time zero, and it grows 8%. And you can see there's the growth in thousands of populations, and they want you to understand what it looks like. Well, it's going to be an exponential curve. Anything that adds a percentage each year is sort of called compound interest, which means it's going to grow exponentially. And that's true for populations, because the more people you have in your country, the more people having kids, and most kids have more than, parents have more than 2 kids. And so you're going to see a growth. And as long as there's jobs and food and whatever, you're going to continue to see growth. Then they go and teach you about half-life. Now, radiation is a big half-life thing. And you can see it's going to go down every 338 days. And that's when you're going to see an X transformation. You're going to see divided by 138 in order to effectively make this half, and we'll go into why that's true in a second. See, right there, it's time divided by 138. We'll go into that. And they go into explaining it. Well, let's look at how they came to that conclusion. So we're looking at 200 grams of a radioactive material, and every 138 days, that's going to become half. So it's going to become 100 grams of radioactive material after 138 days. And it's given by this equation here. Well, it also helps to model these things in your Desmos, always, just to help understand things. So 200 is clearly a Y transformation. And this is clearly an X transformation because T over here is X. What kind of X transformation is it? Well, it's clear the Y transformation is a stretch of 200, but the X translation is easier understood when I write it out as a multiplier of X. It's 1 over 328 times, in this case, T, but T is the same as X. It's much easier when I write it like that, even though you'll see it expressed like this. But it's clear that this is a multiplier of T, and since X transformations do the opposite, so this is a 200 stretch on the Y, but the X is also a stretch. We have a 138 stretch, and why is it a stretch and not a compression? Because it's the reciprocal for X of 138, which means since it's clear that the base here is a half and there's no other transformations, if I have 3 values for the half graph, I can easily just multiply my X values by 138 and divide and multiply my Y values by 200 and graph it. So let's look at a couple values for half of just the half growth. When Y is a half to the X and X is, we'll even take minus 1. Actually, we'll even take minus 2, minus 1, 0, 1, and 2. When it's minus 2, a half to the negative just flips the fraction and becomes positive. So it's going to become 2 squared. And you go ahead in your calculator and figure that out, but you should have studied the last chapters. And when X is negative 1 up here, you just flip the fractions 2 over 1 to the power of 1. When X is 0, the answer is always 1. So there's one of the key things. And when x is 1, you're always going to get your base. And then when x is 2, it's going to become a quarter. Notice the relationship between these and these. They're kind of reciprocals on either side of the 0, which means I can graph them. But if I want to come up with my x values, I simply take all my x values I just had, and I'm going to multiply them by 138. So the first one, which was minus 2, is going to become minus 276. The next one's going to become minus 138. The next one's going to become 0. The next one's going to become 138. And the next one's going to become 276. And the y values are going to be multiplied by 200. So instead of 4, I get 800. Instead of 2, I get 400. Instead of 1, I get 200. Instead of a half, I get 100. And instead of a quarter, I get 50. Which means if I look at this as a graph, y is equal to a half to the power of x. There's my standard decay curve. And then if I look at what we just were looking at, so it's actually to the power of x, how they've written it is like that, right? There we go. I believe I got it. Yeah, that's how they've written it. And now if I pull up the chart for this and I put in those exact values of x, minus 276, minus 138, 0, 130, was it 138? Yeah, 138, and 276. Look at my values of y, exactly as we transform them. So you can see that if you know your base parent function, you can then use your rules of transformation to essentially plot a graph. Very useful skill and something you should get used to. But even looking at this, let's go back to the very basic premise of this and say, okay, what's going on here with that x transformation? Remember that this thing's going to half every 138 days, which means after 138 days I should have 100 grams. And after 276 days, I should have half of that, 50 grams, because we start with 200 grams. And it's clear when this is 0, at time 0, this becomes 0. This half to the power of 0 becomes 1. We have 200 grams at time 0. But at time 1, I don't have 100 grams. I discover that 1, when time is 1 over 138, I get a half to the power of 1 over 138. So I get 0.5 to the power of, open brackets, 1 divided by 38. I get this weird decimal exponent, 0.00072. Half to that is like 0.99. And when I multiply that by 200, I discover after 1 day, my substance is only decayed 190 to 198 grams. In other words, I still have 198.99 grams of radioactive material. But now I want you to pretend, what if I put 138 days up here for time? What happens to that fraction? What happens to 138 divided by 138? It becomes a 1. It becomes a 1. Suddenly I get half to the power of 1, which is just a half. Half times 200, I get 100 grams, which means, as expected, after 138 days, I get 100 grams. Now, what happens after 276 days, which is 2 half-lives later? Well, when I put 276 up here as x divided by 138, I clearly get the fraction 2. Now, half to a power of 2 is a quarter, and a quarter times 200 is 50. So when you see a divider of like here, this divider is usually the half-life, so that every time I put in that full amount up here, this fraction becomes a whole fraction. Whether 1 half-life, 2 half-lives, 3 half-lives, whatever is dividing by this. So if you're told a half-life is a million or 1,000 years, you would put a fraction up here of 1,000. That way an x of 1,000 will create a fraction of 1. An x of 2,000 will create a fraction of 2. It's very good to understand how this fraction of x creates the half-life or growth that you want. It works the same for growth. For instance, if I told you you're going to double your money every 10 years, so you're going to double. I started with $100, and you're going to double it every 10 years. I wouldn't put to the power of x here. I would put to the power of x divided by 10. That's because now if I put in a 10 for x, 10 years divided by 10 is 1. 2 to the power of 1 is 2. 2 times 100 is 200, which means every 10 years I indeed doubled my money. So I've divided that x by 10 up here to create an exponent to suit the 10-year doubling. If things were doubling every 20 years, I'd put x divided by 20. You're going to discover money fractions that get more complicated than this. We're going to get into it more, but that's a good way of understanding how this fraction is influencing x. The same if I wanted to, interestingly enough, wanted my money to double every 6 months. Well, 6 months is half a year, so I actually put 2x in front of there. In other words, it's going to double twice in 1 year, so that when I put 1 as x in here, 2 times 1 is 2. 2 to the power of 2 is 4. 4 times 100 is 400. My money doubled twice, didn't it? 100 to 200, 200 to 400. That's because 1 year there's 2 6 months in 1 year. If I wanted my money to double, or I was told my money will double every month, I would put 12x in here. Right? That way if I put 1/12 as x, 12 times 1/12 is 1. 2 to the power of 1 is 2 times 100. So we see in 1 month it doubled. Whereas if I put 1 year in there, or I guess I should say actually, 1 year, I can say 12 times 1 year is 12. 2 to the power of 12 is whatever, but my money's going to grow astronomically. And suddenly it's grown a lot. You're going to see these big multipliers for things like bacteria, where bacteria are doubling like every hour. And you're going to see fractions when you have to account for things that take longer than a year, like radioactivity and sometimes finance. We're going to skip the negatives because that's not important, but understanding these graphs is really helpful, and they explore it in these examples. Going back to that, if you were asked, okay, when is my radioactive material, which by the way, I'm going to rewrite it here now properly. When does my radioactive material equal to 50, or let's say 25? You can put a y is equal to 25 and find where it crosses, and it'll tell you the x value of when this radioactive material, and by the way, it didn't do it properly, I don't think. No, it didn't. Times, I got to put this half in here like that, I think. There we go. And I discover that my it'll take 414 days to get down to 25, which makes sense because 414 divided by 138 is 4. Half to the 4, power of 4 is 1 over 4, 16th. And 200 divided by 16, I think I might have gone one too many. Yeah, it's 8. So half to the power of, I think I actually even got the division wrong. It's 414 divided by 138 is 3. A half to the power of 3 is 1 over 8. 1 over 8 times 200 is indeed 25. So it's easy to figure out with a graph. If I were to figure it out algebraically, when does this equal 25? Okay, well, I'm going to have to do it algebraically. It's very difficult well, actually in this case it's very easy. So if you're confused by that, just treat it like x. Let's start with that. So you can say, when is 200x equal to 25? When we divide it both by 200, and I get 25 over 200 is the same as 1 over 8, right? 1 over 8. Then I can bring this back and say, okay, can I express this 1 over 8 in a form of a half? So in other words, I can bring this back and say this whole thing is going to be equal to 1 over 8. Well, it's hard to see when a half is equal to 1/8 unless I convert the 8 into something that's related to the half. Well, how is 8 related to 2? It's 2 to the power of 3. How can I express this as an exponent over the half? Well, fortunately, 1 to the power of 3 is still 1, so I can express this whole fraction as this. This is also 1/8. And now it's quite easy for me to say, okay, I've got the same base here. This is a really important rule of exponents. I've got the same base here as here. Therefore, their fractions must equal one another. Therefore, their fractions must equal one another. So I can rewrite this whole thing as this must equal 3. Now I can just treat it like algebra. How do I solve for x? I got to multiply both sides by 138. And then discover 3 times 138 is 414, I believe. And there we discover that it must be 414 days must pass in order for this radioactive material to become 25 grams. So a lot of these will be finding how to make one fraction or one exponent equal to another. Okay, so that would be convert. How would I solve this, by the way? Well, I know 1/8, as I just explained, is the same as 1/2 to the power of 3, isn't it? But if that can replace this up here, I have to include the x. Well, the exponent of the exponent rule says I can just multiply those. And I get this. Since the base here is the same as the base here, it would mean 3x is equal to 8. And therefore, x is equal to 8 over 3 in order for this to be true. You'll discover a lot of this because we're not using logs. It's going to be that. And they do this with cars. Cars depreciate. In other words, they go down in value, which means they're a decay curve. And you do a depreciation. How do you mathematically figure out a depreciation? Well, something is worth 100% in the beginning. And let's say it goes down by 10% in value each year. In other words, let's say I buy a $5,000 car, and when I first buy it, it's worth $5,000. A year later, it goes down by 10%. What's 10% by? So year 1, my car is worth $5,000. Year 2, my $5,000 car goes down by 10%. It's worth that. Year 3, my $5,000 car, that $4,500 goes down by 10%. It's worth this. And so on. But how do I have an equation that will lower this 5,000 to this, to this, to this? Well, we know it's going down by 10%. We know it's going down by 10%. We also know it starts at $5,000. So in the beginning, it's worth 100%, which is 100 over 100. And it's losing 5,000 times 10%, isn't it? Which is 10 over 100. And so we're going to express that as 10 over 100 is 1 over 10. Well, let's just leave it as 10 over 100, okay? And this will work 5,000 times 100%, or 100 over 100, minus 5,000 times that. But notice that they both have a 5,000. So I can factor out that. 10 over 100, 100 minus 100, minus 10 over 100, is 90 over 100. Which means, and that can be simplified as 9 over 10. Which means I have my base now. In other words, notice that it's 90% here. 9 over 10 is 90%, which makes sense because if it's losing 10% of the value, next year it's going to be worth 90% of what it used to be. So suddenly we have a 5,000 stretch, a 9 over 10 base to the power of every year. Now you can, sometimes that's expressed as t, but I'm going to leave it as x. So let's look at this in our Desmos and see if we got it. So we got a $5,000 car that's changing to 9/10 its value to the power of x. And then just to test that out, I can make a copy and pull up the table. And we can see 0, 0, 1, 2, 3, 4. Now sure enough, it follows exactly the pattern that I figured out from my math. You can also rewrite it if you don't want, if the percentages are complicated, you can always say, okay, well, I know it's 100% minus whatever percent it's going down by. Let's say it's going down by 7.36% per year. Okay, and you can just put that to the power of x. And you'll get the same thing. Now let's use the example we just had, which was 10, and see if we get the same thing. And, oh, I had 9. There we go. Now, if I make this red, we'll see it better. I'm going to turn the graphs off. You can see they're the same graphs. So this, I just took 100%. I subtracted the depreciation. I put it to the power of x, because each year, another 10% comes off. But it's clear that this can be simplified to this. Right? But if you get tricky percentages, you can just start with 100 and subtract whatever the tricky percent is, like 5.4334% subtracted every year, and you're going to have the graph you need. Now, you can always put it in simplified format. What's 100 minus 5.34? It's 94.66 divided by 100 to the power of x, and we should get the same graph. And sure enough, we do. So this is the simplified form, but this will help you figure it out. It starts off at 100, and each year we're subtracting a certain percentage. Make sense? That's how they come up with a decimal here, and that decimal is the same thing as the new value. For instance, if I go back, boy, do I still have it? I don't think I have it anymore. If I go back to the fraction I came up with, which was 9 over 10, 9 over 10 can be expressed as 0.9. Anything less than 1 and above 0 will be a decay curve. Remember that. Any base less than 1 but above 0 will be a decay curve. As soon as you get above 1, even if it's a little bit, it's going to be a growth curve. So here's just slightly below 1. Doesn't look like a decay curve until we zoom out. Sure enough, it is. And here's slightly above 1. Doesn't look like a growth curve, does it? Until we zoom out. That's because it's so small and increasing. But anything above 1, growth curve. Anything below 1, decay curve. You just might have to zoom out to see it. And all these are principles that you need to understand. And then they summarize it. 1 minus the decay rate, 1 plus the growth rate is a good way to figure things out. And then they ask you to study all these things, which we're going to get to. Okay, to continue, some of these are fairly straightforward, and I already gave a couple of examples. So we'll look at this, number one, and notice it says to the nearest hundredth of a degree, which means 0, like if the answer's 10, hundredth would be 2 decimals in, so 10.25. And you look to the third decimal to round up this. If this one's 5 and above, you round up this number. Okay, so how do we solve this? Well, here they just want you to practice using your calculator. And so these are pretty straightforward. So in bed mass order, it goes brackets, nothing really to be done there, but exponents, then multiplication. So we have to put that to the power of 10 and multiply by 250. And they just want you to get comfortable getting answers to y, or to whatever a in this case. So x to the y is the 10, x to the y is any exponent, so I do 1.05 x to the y 10 equals, and then I have to multiply it by 250. So that's a. So they're all pretty much that. And what is going on in a? So if I had to guess, because of a, it's a $250 investment that has a 5% growth every compounding period. So that could be every year. And let's say if it's every year, that would be after 10 years, what is that worth? So the answer I just had on the calculator is what's that worth? What's going on with this one? Well, there's a P, so it's probably population. I can see it's halving, so it's something either dying or bacteria being treated with an antibiotic or a virus being treated with a vaccine, and their population is halving. And it looks like it's halving 8 times. So essentially that's going to halve 8 times. But the secret is we take 0.5, which is 1/2, we put it to the exponent of 8, we hit equals. You don't have to hit equals, but I do just to make it clear. Then you multiply by the population that we started with, and we discovered that this population has shrunk to 35.15. Now notice if I double this each time, if I multiply by 2, there's twice, and if I do it 6 more times to 8, I should get 9,000. 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times. So yeah, because it halved 8 times, it would actually be 9 times. So there we go. So we'll do that again. 0.5 to the power of 8 times 9,000. Yeah. So it got, if it was to the power of 1, it got halved once. So it doesn't get back to 9 until I hit the 9th time. That's why. Here we go. And this one, if I had to guess, oh, now they want you to figure out what the multiplier is. So what's the mysterious number missing here? And notice it's a growth of 25%, and it's happening 1 1/4 times. So how do I unravel this? Well, you could look at it this way. If this was all something multiplying n, I could just divide that whole thing out. Since it's something multiplying n, I can multiply it out, divide it out on both sides. Clearly it's canceling here. So n is equal to 500 divided by 1.205 to the power of 1.25. So since whenever you have a missing number that's multiplying anything, it doesn't matter how big and garbled it is, you can just divide that anything out and be left with that multiplier, so long as it's multiplying all on its own and there's no addition to it. Okay, so now all I have to figure out that number is 500 divided by 1.2, don't hit equals here or you'll get the wrong one, to the power of 1.25. That way it'll do the power of first, and when I hit equals I discover that that amount was this. So NO is equal to that, which means it's going to, if that increases 25%, 1 1/4 years, it'll become 500. And then finally, this does the same thing. This is a depreciation. How do I know it's a depreciation? Because this is less than 1. 0.71 is less than 1. That means I have a decay curve. It ended up at 625, which means it's going to start at a higher value. So you can expect P to be bigger than 625. And just like I said last time, that p is multiplying this mess over here. So I can just divide that mess on both sides. And I will get my answer. Now clearly it cancels on this side. So all I have to do is take 625 and divide it by 0.71 to the power of 9. And I should expect a number bigger than 625. If I hit equal sign before I do the exponent, if I hit equal sign right here, I will do a division before the exponent, which will get me way off. So that's why I have to do 625 divided by 0.71, and I have to hit the exponent button now so that it does the exponent first and then divides it in. So that means I started with an amount of principal of $13,000 most likely, and 85 cents. And at a depreciating rate of 29%, because that's what 0.71 is, 0.71 is 100 minus 0.29, or it's 1, I should say it's 1 minus 0.29. So that means it's depreciating by 29% for 9 periods, 9 years, let's say. So it also helps to decipher these things as you go. Complete this table. Okay, so they just want you to recognize different parts of the equation. So decay or growth will all be depending if this is bigger than 1. That's bigger than 1, so that one's a growth. That's less than 1, so that's a decay. That's bigger than 1. It's always the number underneath the exponent 5, not this number. That's a growth. So far we have G, G, D. Now this one is 5/8 bigger than 1 or smaller than 1? Well, 8 over 8 is 1, so that is smaller than 1, so it's a decay. The initial value, meaning when t is 0. So just remember that whenever those exponents are 0, the thing in the bracket will be 1. So the initial value here is 20 times 1. The initial value here is 1. The initial value here is 0.5. And the initial value here is 600. So that's where they all start. Those are all the y-intercepts. Oh, this would be the base. What's the decay rate? In this one case, the decay rate is 1.02, or a 2% increase. This decay rate is a 20%, or 0.8. This one's a tripling, or 3, or if you want, 300%. And this one is 5/8. Hard to put in percentage. I guess that would be, if one is 0.25, I think that's like 0.65 or something. 0.625. Which means it's a depreciation of 37.5%. If your teacher wanted you to analyze it further. But the base is good enough. Here's a small town, starts in 1996, given by this function. First of all, always figure out what the population is when n is equal to 0. That's easy because this will always become 1, which means the population starts at 1250. Is it going up or down? Is it a growth or a decay? That's over 1, so it's going up. So I've answered A by accident. A says, what's the initial population? That's when this is 0. If that's 0, that becomes 1. Anything to the 0 becomes 1. And anything 1 times that's going to be that. So the initial population is 1250. What is the growth rate? It's 3%. 1.03 is the base, which is a 3% increase over time. How do I know? Because if I take this, it's over 1. If I subtract 1, I get 0.303, which is the equivalent of 3 over 100, which is equal to 3%. 1 would just mean nothing is happening. So anything over 1 is the growth rate, I guess. Determining the population by 2007, well, you have to realize that this represents year 0. So 2007 would be 2007 minus that, which is 11 years, which means I have to put an 11 in here. So I do 1.03 to the power of 11, 1.03 to the power of 11. Times the initial population. Whoops, I accidentally put that to the power. There, population grew to 1,730.3 people, or if you want, 480 new people in 11 years. What year does the population reach 2,000? It's a much more interesting question because this 2,000 is on the y side of it. So when does 2,000 equal this? So I have to isolate this here. It's being multiplied by 1250. So divide both sides by 1250. It disappears here. And I get 2,000 divided by 1250. .6. So I have to figure out when this becomes 1.6. Hang on. There we go. And you could try to figure out how to make this 1.03, but it's going to be very difficult. And the easier thing to do is take 1.03. Well, I'll show you the log method, which you won't learn until next year. But the official accurate way is we're going to take a log of both sides. And they shouldn't be caps lock, but whatever. And when I take a log of both sides, the rule for logs is I can take this exponent here and put it in front as a multiplier. You'll learn this y later on. And now remember the equal sign is between these things right here. So to get rid of this, get n all alone, this is just a number. Divide both sides by that. And I can get the exact n by that, 1.6 log, but you're not going to learn that till next year, divided by 1.03 log. Ignore what's going on in the background. And I get 15.9. Now notice that it would have been very hard for me to come up with that. 15.09. So let's keep that in mind. Okay. To do it this way, the long way without the right math, I have to guesstimate. So first I'm going to do this. Remember that when I divided this out, I get 1.6. And keep in mind that this is the actual answer that we already figured out. To do it without exponents, I have to take 1.03, and that's to the power of 1. And if I multiply by itself, if I hit times and equals, that's the power of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's just below it. So that's to the power of 15. And here's power of 16. And I immediately see that power of 16 is above it, and power of 15, because I'm trying to get to 1.6, and it's clearly in between. It looks like it's very close to this. So at that point, you do, okay, well, 1.03 to the power of 15.5, and you go, oh, too low. And you go, okay, well, clearly it's much higher, so 1.03 to the power of 15.5. let's say you guess at 9, and you go, oh, that's really close, probably 0.9. And you have to sort of guesstimate, which is it's a pain. The only other way you could try to do it, and you can't really, is to somehow put this to the base of 1.03 to come with an exponent to see if to make their exponents match. And that's kind of what we're doing when we're doing this guesstimate. The other way is put it in a graph and find out where 2000 on the y-axis, what x value that is. But the log is a fantastic way to see if you got it right. I would strongly urge just memorizing that log thing just to verify your answers. Okay. The computer is losing its value. What is losing? Decay or growth? Losing is decay. Its value is modeled by this. So its value is going down based on months. Each month it loses 5%. How do I know it's 5%? Because that's 0.95, that's 95%. So it means it's losing 5% each month. What is the initial value of the computer? Well, again, when that is 0, this is 1. So the initial value of the computer is $1,500. What is the rate of depreciation? It's 0.95 is equal to 1 minus x. So x is equal to negative 0.5. 0.05, which is 5% depreciation value. Determine the value. So if you want to do that algebraically, you do, okay, 0.95 is my result. It's equal to 1 minus a value. If I put if I subtract 1 on both sides, I get negative 0.05 is equal to negative x. When I divide by negative 1, I get x is 0.5, which is 5%, which means my depreciation is 5%. It's going down by 5%. But that's very obvious when you realize that this is 95%. Determine the value of computer after 2 years. That's simple. We put a 2 here. So we put 0.95 to the power of 2. And then we multiply it by the initial value of the computer. And after 2 years, the computer, if I were to resell it, is only worth this much, $4,512. Depreciation is a very real thing, and almost everything you buy depreciates, with except right now real estate, but everything else depreciates. In which month after it is purchased does the computer fall below? When does it? So this is nice because they only want to know below, so they don't want the exact. But what's interesting, the question is, when will $900 equal this equation? So first I divide 1,500 by both sides. And I get 900 divided by 1,500. And I get this nice little fraction, 0.06. So now I've got 0.6. So I got 0.6 is equal to this. And if I had my log ability, right, I would now take a log of both sides. So I'm going to do it over here. Take a log of both sides, and I end up with log of 0.6 is equal to m times the log of 0.2595, because the exponent can come down, which means that m is going to be equal to log 0.6 divided by log of 0.95. So I can get an exact value this way. And if I take it, 0.6 log divided by 0.95 log, I get this nice 9.95. So m, month, which month? Because we're working in months, remember? So that means m is exactly equal to this. So that's when it's going to hit the value of what did it say? 400? 900. So that's when it's going to hit 900. And it says what month does it happen when it is below 900? Well, it's clearly month 10. But if I'm going to do it old school, I have to take 0.95 and multiply it by itself. They're squared to the 3, to the 4, to the 5, to the 6, to the 7, to the 8, I'm close, to the 9, to the 10. There we go. 10th month is the first time it falls below the dollar value we mentioned, $900. So and that's how you do that. And they keep going like this, and they get a little bit more complicated as they go. And obviously the extension gets very hard. This starts to get into where annuities come from. Don't know if I'll be able to do all of these, but you know, I can try to do some of them. I'm going to do this one and then take a break. So how do I do A? What's the growth rate? Well, let's do the amount is going to be equal to the principal, and it's growing at 6%. So it's 1 plus 6 over 100, which is 0.06, to the power of years. So what's the growth rate? The growth rate is 6%. What is the initial amount? The initial amount's $1,000. How many growth periods are there? 15. Write an equation that models the growth of the investment and use it to determine the value of 15. Okay, so here's the equation. We have the principal amount. Since it's growth, it's over 1, and we just add the percentage to 1. And we put however many years there. Now, since we're doing 15, I'm going to take 1.06 to the power of 15. And then I multiply that by the initial. Notice that your money will more than double. 1,000. And so that means if you can find an investment that grows at 6%, after 15 years you'll have $2,300. And if you look at your initial $1,000 investment, it means you made $1,396.56. So your money more than doubled. Bacteria generally decays. And I can tell you right now this one's decaying every 10 years because it's doubling. Sorry, not this one's doubling, and it might be, oh, it looks hours. So every 10 hours. So every 10 hours this is doubling because I can see the divider there is 10. And we can work out how I can figure that out. So bacteria starts with a population of 500 noon. It doubles every 10 hours. There we go. The function is modeled by this formula, where P is the population based on the hour, and T is the hours. Y is the exponent over 10. Okay, well think about it. If 10 hours passes for T and I divide by 10, I get 1. And 1 multiplies, that means 2 to the power of 1, which means it will double my 500 whenever that's a pure 2. So when that is 10 for time, it'll double. When it is 20 hours, that'll be 2 to the power of 2, so 2 to the power of 2 is 4, and it will double it again, so it'll go to 1,000 to 2,000. The reason it's 4, because it's 4 times the initial value to figure out the doubling of the next value. But just every 10 hours, this is what it's gonna look like. The first 10 hours, it's gonna double once. The next 10 hours, it's going to double. That new population is going to double. The next 10 hours, that last population is going to double. You can see how quickly things are growing. And that's the interesting thing. The bacteria and virus are the dominant species on the planet, mostly because their ability to repopulate is unprecedented. Why is it the base of 2? That tells me this is going to double every 10 hours. Why is the multiplier 500? That's because the initial population of the bacteria is 500. So when this is 1, in other words, when T is 0, this becomes 1. And that's the initial population at time 0. Determine the population at midnight. Well, let's see. It starts at noon, 500 at noon. So midnight is 12 hours away. So that means right here in this formula, I would put a 12. So right there, I have to put a 12. And you might say, how do I do a 2 to the exponent of 12 over 10? Well, If you have to use brackets, go ahead, but you do 2. You press the exponent button. And go ahead and open the brackets so that it solves the fraction on its own. And it's obvious that 12 divided by 10 is 1.2, but I want to show you how to do it. And then when you close brackets, there you go, that's 1.2. You click equals, it does the exponent. So that's 2 to the power of 12 over 10. And then when you multiply it by 500, you discover the population of the bacteria has more than doubled, slightly more than doubled. Which makes sense because at 10, it would have doubled perfectly. So it's clear that at 12, it's going to do a little bit more than that, right? Determine the population. Right? Determine the population at noon the next day. Okay, so how many hours is noon the next day? It's 24 hours. So this up here becomes a 24. And it's the same thing. You're going to take 2 and you're going to clear your calculator. You're going to take 2. You're going to press X to the Y. You're going to open brackets. And you're going to hit 24 divided by 10. Then you're going to close the bracket so it does that fraction. Then you're going to hit equals. You don't have to. You could just multiply by 500. Hit equals. That's how much it's grown. When I multiply it by 500, I see that the new population at 24 hours is equal to this, which makes sense because at 20 hours it would have doubled twice, and at 30 hours it would have doubled again. And determine the time at which the population is equal to 2,000. Well, I accidentally did it there. And I can do it because after 10 hours, this will be 1,000, and 10 hours more, it'll be 2,000. But if I wanted to do it legitimately, you would put this where the population is. The first thing you do is divide both sides by 500. So this clearly becomes a 4. And the nice thing about a 4 is now I can figure it out exactly. Yeah, so keep in mind that this is a mysterious t now. We don't know the t over here. All right. But the nice thing about 4 is I can put 4 exactly as a base of 2. 2 to the 2 is equal to this to the mysterious 2 to the t to the 10. Now, when the bases are the same, their exponents must be the same. That's just a logical rule. If I said to you 3 to the x is equal to 27, then you realize, okay, I can express 27 as 3 to the 3. It's clear that the only way this can be true is if x is equal to that. Okay, well in this case, the only way this can be true is if 2, this exponent here, is equal to this exponent here. To solve this, I multiply by 10. So 2 times 10 is 20. So therefore the time is 20 hours for this population to reach 2,000, which is what we knew already. Just got to take a break. Okay, we're going to continue here. All the questions are fairly similar. They're always going to be a growth or decay. Explain why these are exponential decay. Which of these are exponential decay? So the definition of decay is anything where the base is between 0 and 1. That's a decay. Anything above 1 will be a growth. And it sort of makes sense because if I multiply, let's say this is less than 1, if I multiply it by itself, it gets smaller. It gets smaller. Anything less than 1 multiplied by itself will become a smaller number. In other words, it will decay, it will go down. Anything above 1, so let's take 2, or even 1.1 times 1.1 is 1.21. Anything above 1 becomes a bigger number when it's multiplied by itself, thus it will grow, or a growth curve. So all we have to do is identify the base to determine which is a growth and a decay. Now don't get deceived by these numbers in front. Those are transformation numbers. Whenever you want to identify what you're dealing with, look for the x. So here's the x, and we know we're dealing with exponentials. So the x is always going to be above the base. What's the base here? It's 3. Is that below 1? No. So that's a growth, so it's not a decay. Here's the x, so that's the base. Is that base above 1? Yes, it is, so it's not a decay, so we cross it off. Here's the x. Now be careful, you might say, oh, there's a 2 there. But that's part of the exponent. So you have to look for the base. Is that less than 1? Yes, it is, so that's a decay. Here's the x. Yes, it's transformed, but that's part of the exponent. It's above the 0.9, so that's the base, 0.9. Is that less than 1? Yes. So C and D are decays. And it's all to do with the base, always. Transformations have only impacts on the domain and the range, not on the actual parent function. So here we have a town of a population of 12,000 that has a growing average rate of 2.5%. What is 2.5% as a digit? It's 0.025 for the last 10 years. So for 10 years now it grows at 2.5%. Suppose this growth rate will be maintained in the future. The function that models the town is this. Now ask yourself, why is it 1.025 and not 0.025? Well, 0.025 is a decay. It's less than 1. This town is growing. So if you're growing by 2.5%, your town is increasing by 102.5%. The 2.5% is how much the 100% is increasing. Or thought of another way, the town is increasing by 100% each year plus another 2.5%. And if we add these as decimals, 100% as a decimal is 1, and 2.5% as a decimal is 0.025. If we add them, we get 1.025. So that is definitely above 1, which makes sense, and it's a situation where something is growing by 2.5%. What about the 12? Well, they tell us that the town is modeled in thousands. So that 12 represents 12,000 people. So whatever population we figure out at the end using this 12, if we come up with like 14, we have to add another 1,000 to it to say, well, it's grown to 14,000, because that 12 represents 12,000. That's what they mean when they say where P of n represents the population in thousands. It means at the end you have to multiply by 1,000. And n is the number of years from now. Okay, so that's the number of years from now. That's the 12. Let's just stop for a second and ask ourselves, what transformations are there? Well, first of all, this is a growth curve, because it's 1.025 is bigger than 1. Second, the n is equal to time in years, right? And third, the 12 represents a stretch, and it's outside of the x, so it's a vertical stretch. It's a y transformation. So if I was going to find new digits, and you might say, well, how would you account for this stretch in here? Well, here's the stretch in there. If I was to rewrite this as a proper transformation, it would be this. The 12 is fine, but inside it's a 1 times, it's a 1.025. Let's see. Let's say it's a growth of 2. Let's take 2 to the x, like that, and ask ourselves, what do I have to multiply 2 by to get 1.025? Well, you would say you just take 2 and divide it by 1.025 to get that answer. And the answer is 1.95 whatever, which means if I was going to rewrite this properly, I don't think that was right actually. So you have to take 2 and divide it by 1.025. And I get that. So if I multiply that by 2, no, that's not right. So I have to take 1.025 and divide it by 2. So that means if I multiply 0.5125 by 2, that's what I'll get. Which, I know this sounds weird how I'm doing it, and you can skip it if you want. But if I was to write it in perfect transformations, it would be this. So that I could say, okay, well, I'm dealing with the parent function of 2, and I have an x transformation that is essentially that over 10,000 as a fraction, which is clearly less than 1, which would normally be described as a compression, except we know that the actual thing that's going to happen is a stretch. You have to reverse it for the x, which means if I was going to transform my parent function here, I would find all my parent functions of this, and I would multiply all my x values by that and all my y values by that. And that would give me the two new transformations. So as an example, I know the base on the parent function of 2 is 0, 1 and 1, 2. So the x value would become whatever 10,000 divided by whatever that is, flipped. So it would become that. So this one would still be 0, but the y would be 12. And this one would become this. And I'll just do it there, repeating. And the y would become 24. So you could expect to see these 2 points on this graph if I was going to write it in a way where I needed to transform it. Sounds confusing for sure. We'll see if that's true. We'll just keep those 2 dots in there. But let's just ignore that. Determine the population of the town in 10 years. Well, we just put 10 in for n, right? So we're going to do that. 1.025 to the power of 10. And we got to multiply by 12. But just remember that this is a population that hasn't been multiplied by. So in 10 years, the population is this, but it's really 15,361 people. You ignore the rest because we don't deal in fractions of people. So that's the population in 10 years. Determine the number of years until the population doubles. What was the population to start? It was 12. Okay. What's the population going to be when it doubles? 24. So you're dealing with this to the power of n. And first we divide both sides by 12. And you're dealing with this, which makes sense because we're looking for the population to double. Now this is very hard to solve without logs. I'm going to show you the grade 12 solution. We take a log of both sides. The rule of logs says I'm allowed to bring that exponent down. That's why we learn logs later on. And a log of a number is just a number. So now we're going to divide both sides by that number. And we discover that n is equal to log of 2. So you press 2. Sometimes it's log first, but in this case it's log 2 divided by 1.025 log equals. And we discover it's 28.07 years. But to figure that out logically without logs, it's clearly difficult. So we'll keep that in mind. And you have to do a lot of guesstimates. Well, we discovered earlier that 10 years, the town was 15,000. So we know it's more than 10 years. Now, it's hard to just jump to that, but you essentially have to put some guesstimates in there and say, well, 1.025 would have to multiply itself quite a few times to reach 2. And yes, we could sit there with a calculator, but it's a big pain in the butt. I think you're better off to just say, okay, I'm just going to start with an arbitrary number like 40 and see if it doubles to the power of 40. Oh, and it did. So we know 40 is too much. Then I'd go down to 30. And I would take note at 30 here. Wow, that's really close to 2. So I'm going to go down to 25. And I'm going to quickly notice that I'm close. So 25 at 25, I'm now just going to multiply it by 1.025, which is the base. And that's going to be 26. And if I click equals again, it's going to be 27. If I click equals again, it's going to be 28. We haven't quite reached there. So the first year it does pass is 29. And that makes sense because at this point, this is 28.07. It represents some part of the way through the year. But at 28, it hasn't quite reached there yet. So the actual answer is the first whole year, the year that it occurs, is 28. But the year when it first happens, or which first goes over 2, is 29. I think technically you would answer 28 though, because it's happening within the 28th year. 29 is too much. Use this equation or another method to determine the number of years ago that the population was 8,000. Oh, so when was it smaller? Well, it's okay. What's 8,000 in this situation? 8,000 would be a population of 8. So it's still the same thing. We divide both sides by this. And you get 8 divided by 12, which is 2 over 3, which is 0.66. Now, clearly, this number is smaller than 1.05. And if I keep adding bigger numbers, this is going to get bigger. So this must be a negative number. Now, you can still do the same log thing, and you end up getting log 0.6666 divided by log 1.025 will be equal to n. So that'll give us a good idea. And we should get a negative number. So we discovered roughly 16 years back. We discover this, which is equal to 16.4 years back, roughly, is when it happens. But if we can't figure this out, and there's no way to really take a square root with the n in there without knowing n. We can't just square root both sides. But we can take the same sort of guess. We can take 1.025 and put it to the negative 10. And we discover we haven't gotten small enough. So we can take 1.025 and put it to the negative 20. And we get 0.6. And we notice it's somewhere between 20 and 10 and quite close to 20. And then you can just divide before we were multiplying. Well, you can go to 15. Let's go to 15 instead. 1.025 to the negative 15. And we discover we're close, 0.69. We're trying to get to 0.66. So now you can just divide by 1.025 instead of multiplying. So that was negative 15. Here's negative 16. Here's negative 17. So it's happening between 16 and 17, just as our original thing pointed out. So between 16 and 17 is when it's happening. So just over 16 years back, it happens. And we divide that way time because we're going backwards in time. We multiply if we wanted to go forwards in time. Kind of complicated. What are the domains and range of this function? Well, since we're talking about real time, but they just went back in time. So I'm going to give you since they did go back in time, it's kind of weird. But anyway, normally, just as a function, the domain is always XER. And the range depends always if there's a vertical adjustment up here. And if there's a minus in front, we're going to have a decay curve that looks like, instead of looking like this, it's going to look like that. Well, there's no minus in front, so it's just got a normal domain upwards from wherever this is. Well, there's nothing there, so that's really plus 0 here, which means this domain here, this range rather, is y is bigger than 0, which is the case with all growth and decay functions. Now, if they were dealing in real time and said 1996, which is when this function started, actually they didn't really give a year when it starts, so time is, the domain is still xer. But if, let's say, it was a bacterial growth, then you would only ever have a bottom end where time is 0. And then the limit to that is always infinity. So its domain would then be 0 smaller or equal to x smaller than infinity, because it's never smaller or equal to infinity. So those would be real-time situations where they put a time limitation at the bottom end. In this case, because they asked us to go back in time, they didn't really put a time limitation on. All right. Number 9. A student records the internal temperature of a hot sandwich. Now here's a little bit of science for you. If I leave an item that's hot in a room, there's a little trick to understanding what the maximum temperature that sandwich is going to be left in. If I leave an item that's boiling, 100 degrees Celsius, in a room that's 22 degrees Celsius, guess what? This coffee, if the room is bigger, obviously the volume of the room is much bigger than the coffee. That means this coffee is going to cool down. And the room is going to heat up a tiny bit, but depending on the volume of the room versus the volume of the cup of coffee, it's not really. So slowly this coffee is going to cool down until it reaches the room temperature. Now, interestingly, if I put a cup of coffee that was 1,000 liters or 10,000 liters in a room that was also 10,000 liters of air, even though this isn't quite accurate, the coffee will cool down, but the room will heat up, and they'll meet somewhere in the middle because they have equal volume, so there's equal weight to their values. You add them together, 122 divided by 2. They're both going to reach a temperature of about 61. So you can actually heat up a room, which is what they do with hot water radiators, right? Hot water radiators are constantly feeding in the same temperature of water. The water never cools down because it's coming from the furnace, and they heat up a room. And actually all heating works that way. You're putting in a heater that doesn't cool down, so it's slowly heating up the volume of the room. As soon as this heat turns off, your room will match the outside temperature, because your outside world is a much bigger volume, right? That's why we use insulation in Canada and insulation in just about everywhere, and why they don't use insulation elsewhere. Although technically insulation also keeps things cool. So people should really use insulation everywhere. What's the temperature of the sandwich once you begin recording? Well, that's time 0, isn't it? So let's look at this formula. Before we start, let's look at a couple things. This plus 19 has raised the entire graph, which would normally look like this, and it would normally hug the x-axis, right? All decay curves would hug the x-axis and never quite reach it. But this thing has been raised 19 above. It's been raised 19 above the x-axis, which means there's an invisible asymptote right here at y is equal to 19. Why is that? Why will it never quite get to 19? Because in this case, 19 is the room temperature that we're cooling down. So I actually will know, and then there we go. Here it is right there. So it'll never get colder. It'll only reach the room temperature. How do I know it's decay? Right there. That's less than 1. How many hours do I realize where's the starting temperature? Right there. Because if this is 1, actually no, it's starting temperature, if this is 1, 63 plus 19, the starting temperature of the sandwich is going to be 82 degrees Celsius. That's the starting temperature of the sandwich. And it's going to cool down to 19 degrees. Now, how long would it take for this heat to half? Well, it's going to half when this fraction here is 2. But this fraction is equal to 2 over 10. So when will that exponent, be equal to 2? Multiplied by 10, when time is equal to 20. So we can see, because at 1, actually it's going to first half when this fraction's 1. Sorry. And when will that happen? At time is equal to 10. So it's first going to half in temperature. 10 is it hours? Minutes. So 10 minutes from now, this temperature is going to go down by half. And 10 minutes later, that new temperature is going to go down by half. And 10 minutes later, that new temperature is going to go down by half. Until this slowly reaches 0, and the room temperature left will be 19. But to figure out the initial temperature, we put in a 0 here. So I'm going to put in a 0. 0 over 10 is 0, so that whole thing becomes 0. 0.5 to the 0 becomes 1. 63 times 1 is 63, plus 19. Initial temperature is 82 degrees Celsius. So what was the temperature of the sandwich when she began to record the temperature? 82 degrees Celsius. Determine the temperature to the nearest degree of the sandwich after 20 minutes. Okay, that means we put a 20 up here. What's 20 divided by 10? It's 2. What's 0.5 times to the power of 2? 63 times 0.25 plus 19. What's 63 times 0.25? It's a quarter of it. What's half of this? 31.5. What's half of that? 15.5.7. I think it's that. 15.575. So that's that. And we add 19. 19 plus that is 34.75 degrees Celsius. And it says to the nearest degree. So we round this up to 5 because the digit after 4 is 7. So this becomes, so it's 35 degrees Celsius after 20 minutes. Okay. How much time did it take the sandwich to read an internal temperature of 30? Well, in this case, they're telling us the final result of 30. So I'm going to put that where temperature is. And we have to unravel the equation here. And let's do it. Let's just get rid of everything here. There we go. What's our first step? We have to subtract this 19. It's sort of reverse bed mass order. So we subtract 19 from 30. We get 30 minus 19, 11. What's the next step? We have to divide the multiplier out because it's reverse bed mass order on both sides. It cancels here. So we're looking for when this whole thing is going to be equal to this. Now the easiest way to solve this is first find that fraction. 11 divided by 63. That's this fraction here. Whoops. The next thing you should do is, instead of working with that complicated exponent, just pretend for a moment we're going to make this x equals this. X, t over 10 is equal to x. And we're just going to put an x over there for now. So now I just need to find what exponent, how many times does 0.5 have to multiply itself to get that? Well, the easiest way for me to do that is to take 0.5, hit the multiplication sign, and when I hit equals, it'll be squared. When I hit equals again, it'll be cubed. When it hit equals again, it'll be to the power of 4. And I see that I've already passed it, right? And that means I'm dealing with, as I suspected, a complicated fraction. So it becomes very hard. So I got to go back and try it again. So when I multiply by itself, that's squared. I'm almost there. So it's between 2. So it's between 2 and 3. This is going to be between 2 and 3. So let's try 2.5. We're going to take 0.5 and put it to the power of 2.5. Oh wow, very close. I need it a little bit smaller, so I'm going to multiply it by 2.6. It went down too far, so it's 2.5 something. I'm going to do 0.5 to the power of 2.55. Very close, but smaller. I'm going to just try to get it as close as I can. 0.5 to the power of 2.52. That's about as close as I'm going to get. 2.52. So that means x is 2.52. Now I'm going to bring back my fraction. And now that I know x is equal to this, I'm going to go like this. I multiply by both sides, and I get t is equal to 25.2. And if I'm going to just give a rough estimate, it's roughly 25. And what's 0.2 of 60 minutes? Well, it's 12. 25 hours, and 0.2 of 60 seconds is 12 seconds. So that's roughly the time it takes to reach that temperature. To do this algebraically properly next year, we're going to take this situation right here. I'm going to take the log of both sides. So this is going to come down. And I'm going to get an exact one. It's going to be the log of this divided by the log of that. And I'm going to use this fraction up here. So I'm going to take 11 over 63 to get very accurate. I'm going to take the log of it, and I'm going to divide it by the log of 0.5. And this is going to be my x. So my x is actually incredibly accurate. We were close. We had 2.52, but my x is actually 2.5178483, like that. So now I can take my really accurate x and substitute it over here where t over 10 is equal to that. And when I multiply it, I get t is equal to, both sides by 10, 25.1784. Now, that 25 is in minutes. And that 0.784, so I'm just going to take 0.1784 and multiply it by 60 to get the seconds. It's about 10.7 seconds. So I get 10.7 seconds. Almost 11 seconds. We were pretty close. We had 25 minutes and 12 seconds. So notice that we get more accurate if we can do the algebra, but we got pretty close. And that's how, unfortunately, you're forced to guesstimate when you don't know logs. And then these are all the same, 10, 11, 12. Write an equation that describes the system. Okay, percent of color left of blue jeans loses. So what's something that goes down or loses? It's the decay. If it loses 1%, it maintains 99%. So one way you can look at it is if I start with blue jeans and I call it 100%, and it's going to multiply by 1 is going to be, or 100%, which is 1, it's going to maintain it. going to maintain its 100%. But if I'm losing 1%, what's 100 minus 90? 100 minus 1%? 99%. Now you can also, which is 0.99, right? You could also do it this way. You can convert them to fractions now. What's 1 minus 0.9? 0.101? It's 0.99. So now, for every time they're washed, x will be equal to the time they're washed, where x is equal to the time they're equals to number of times washed, and percentage based on x will be the percentage of color, and p of x is equal to the percentage of color left. Now, you can also change this to, let's say you have a scale of blue. You can replace that with, let's say it's 1,000 on some sort of scale. You can replace that with any measurement that would measure how these blue jeans are fading. And you can see that this works. And so we're essentially, let's say we do the jeans 5 times. We wash them 5 times. We multiply by 100. And the jeans are now at 95% of their color. Okay, so that's that one. If the population of a town has 2,500 residents, so we have 2 choices. We can start with a multiplier of 2,500, and it grew at the rate of 1%, so it's 100%. Sorry, it grew at the rate of 0.5%, which is 0.5%. If we put these into digits, 100% is 1, and 0.5% is 0.05. That's tricky. So when you add them together, you get this. So that's our ratio, and it's t. And now our population based on time is going to grow very slightly based on that. Now you can also write this, and how you would explain this is population P of t is equal to the population based on years past, and t is equal to years past. Now keep in mind you could also write it as 25 times that, and then you'd have to say your P of t is in thousands, so that you can tell people to multiply by 1,000 after. And here's a bacterium growth. It takes 1 day to divide into 2 the population after t days. So dividing into 2 is doubling in size. So you have a population based on time that's going to be equal, and it's whatever the population of the colony is, let's call it population initial, times 2 to the power of t, because they didn't give us the population initial. And then we would just explain it. P of t is the population based on the passage of time in days. T is equal to the time in days. And pi is equal to the initial population size, whatever it is. 1,000 bacteria, 50 bacteria, you would have to substitute a number in here, whatever your bacteria population, your initial population is. All right, so that was just kind of hypothetically working on questions. So here we have yeast is doubling in 1 hour, and it starts with 80. So let's pretty much what our last thing is. Doubling means we have a base of this. Our t is going 2 to the power of t, where t is equal to hours, right? What's our initial, and we want to put a bracket around that. What's our initial population? It's 80. And we're pretty much done. Our population based on time is equal to 80 times this. If t was 0, right, this would become 1 times 80. If this is 1, it's 2 times 80. So in 1 hour, we get 160, which makes sense. If this was 2, we get 4 times 80, which is 320, which also makes sense. It doubled again. So there we have that. What is the growth rate in percent per hour of this colony? Well, it doubles. So it's 200%. You might be tempted to say 100%, but 100% is just 1. So work backwards. 2 is going to be equal to 200%. So the growth rate is, or you could say, increases by 100%, which is essentially saying 100% plus 100%. Depends what your professor prefers. Write an equation that can be used to determine the population after t hours. Well, we did. Use your equation to determine the population after 6, so we put a 6 in there. 2 to the power of 6 times 80 gives me a population of 5,120. So after 5 hours, I have a huge population. How many times bigger than 80 is that? It's 64 times bigger, which makes sense because 2 to the power of 6 is 64. Okay. Use your equation to determine the population after 90 minutes. So be careful because we're working in hours in t. So what is 90 minutes in hours? It's 1.5 hours. So you have to be careful in these questions. So 2 to the power of 1.5 is equal to that. And then you got to multiply it by its initial population. So the population is now 226. So that's for D. Approximately how many hours would it take for the population to reach 1 million? Okay, well, that just means they've given us the population. These questions are always harder. And so they're asking us for when it's going to be 1 million is equal to 80 times 2 to the power of t. Well, our first step is to divide by 80. When I divide by 80, the 1 0 disappears. Or I can just take 1 million and divide it by 8, but either method will work. So I get this. So they essentially want to know how many times does 2 have to multiply itself before it reaches this. Well, I can start off with a simple one like 2 to the power of 15 to see if I get close. I went way over. So let's do 2 to the power of 10. That's 1,024. I'm just going to multiply that by 2, and that's going to be 2 to the power of 11. Then I'm going to hit equals again. 12, 13, 14. So it's somewhere between 13 and 14. Somewhere between 13 and 14. And probably about halfway between. So I'm going to do 2. I'm going to do 2 to the power of 13.5. And I get pretty close. It's a little bit higher. So 2 to the power of 13.7. A little lower. So 2 to the power of 13.6. Pretty much bang on. So it's probably t is equal to 13.61, something like that. Well, that's 13 hours, and 0.6 times 60 will give me the minutes, which is roughly 36 minutes. And I can get even more accurate. But let's use our log method now. Let's use our log method to see if we can get close. And we'll just put this aside over here. Now our log method says if I take this population here, and I'm looking for 1 million, which is then divided by 80, I get this. And if I take the log of both sides, I'm allowed to take this exponent now and move it down to in front. And now t is multiplying this number, because a log of a number is just a number. And I divide both sides by that number. And on the right side, it disappears. So I get t is equal to log of 12,500 divided by log 2. So I take 12,500 in my calculator. And sometimes you got to press the log first. And I'm going to divide by 2 log. It equals. And look at that, I got very close. T is actually equal to this, which is 13 hours. And now I'm going to take that decimal and multiply by 60. So I subtract 13 here. Multiply this by 60 to get the minutes. And this is important too. So it's that many minutes. And I can take this last decimal, subtract 36 here, and multiply by 60 again to get the seconds, 34.7. So in 13 hours, 36 minutes, and 34.7 seconds, I will reach a population of 1 million yeast cells. You can see that the logs are quite good, although to our credit, we came up with a somewhat accurate answer, especially since they say approximately. What are the domain and range of this situation? So this is a good question. We have to be careful because in a real life situation, our time will never go down below 0. So that means 0 is smaller or equal to t, which is smaller than infinity. So that's our domain. Our y, I can see that there's no y transformations, and there's no negative in front of the 80. So y is bigger than 0. If you want to get a good idea of what this looks like on a graph, always go to your Desmos. Now, I've got to put a t in here. There we go. And you'll discover at time 0, you're going to have 80 population. So clearly you'd never go back in time because we started with this. So that means we're only dealing with 0 is smaller or equal to x is smaller than, well, you just write it like that. You don't need the infinity. So, sorry, t. I got to put it as t. And it helps if I stretch out my y-axis or my x-axis. There we go. Oops. What happened to my... There we go. And there we go. Now we get a good, better idea of how this thing is growing. Now the nice thing is, if I wanted to find that $1 million answer on a graph, I would just do this. And now I have to go way up on the y-axis. And there it is. And I find out where they cross, and there's my 13.61 hours. And you can find any population much faster and easier graphically. All right, let's go back. A collector's hockey card collection he purchased in 1990 for $5. The value increased 6% every year. So let's look at that as a thing. If I start off with something that's worth 100% and it increases by 6%, and I convert those to decimals, I clearly get this. So that's going to be the base. And and we're going to put it to the, what was the initial value? It's $5. And it increases every year, right? Yeah, 6% every year. So that means the new value, based on time and years, is going to be equal to that. Write an equation that models the value of the cure, giving the number of years, 1990. So 1990 represents year 0. Determine the increase in value of the card in the 4th year after it was purchased, from year 3 to year 4. Don't quite get that. Determine the increase in value of the card in the 4th year. So I guess they want to see how much was it worth in year 3 to year 4, so how much did it go up? So we need to find year 3 first. So we do 1.06 to the power 3 times 5. So in year 3, and we got to round up properly. So the value in year 3 is equal to this, but we have to round this up to 6, so it's $5.96. The value in year 4 is equal to, so it's 1.06 to the exponent of 4 times $5. And then you got to round up to the nearest cents. It's this. So the increase from year 4 to year 3 is equal to V4 minus V3. So you take this, you round it up, and you subtract the previous year's value, and it increased in 35 cents. Determine the increase in value of the card in the 20th year after it was purchased. By the way, in year 4, how much did it increase? 6.31 minus 5. It increased in value $1.31. And then they want to know the 20th year, so we'll do for 20. And what do we do for 20? We just put a 20 in for time. So we do 1.06 to the exponent of 20. And we multiply by its 5. And we get this. So the value in year 20 is equal to this. But we have to round it up right there. Becomes a 4. It increased in value by $11.04. $11.04. Collector, we did that. Light intensity, yeah, you're going to see this. As you go down into a lake, this is actually a science question, and you'll find in a lot of science classes, so do it. When you go down into a lake, the light gets less. You'll notice this if you ever scuba dive, or even if you just jump down into a lake, it gets darker. That's because light gets reflected more and more as it goes down, and especially different wavelengths. I think it's blue. Is it red or blue that hits depth? And after a while, nothing goes down. But it goes down 9% for every meter of depth relative to the surface. Write an equation. Well, the going down is a decay. So it's going down by 100% by minus 9%. So it's 91%, which is 0.91. And it's going down for each meter that we go down. And it starts off, what's the light at the very top? 100%. It's 100%. So that means the light intensity based on depth is equal to that. Right there it says assume it's 100% at the surface. So 0 here is the surface. That makes this 1. That makes it 100%. So we can even put a little percent sign here if we wanted to. But 100 will do. Determine light intensity of 7.5. So we put 7.5 in for the depth. So it's 0.91 to the exponent of 7.5. And that's how much it shrank. And we multiply by 100. So that means our light intensity at 7.5 meters is equal to 9.3%. So we've lost half our light at 7.5 meters. This disinfectant is advertised to kill germs at 99% with each application. So that means it reduces the population of any germ base by 99%. What's 100% minus 90%? It's 1%. What's that as a decimal? Like that. So if you have 100% germs, and you multiply it by 0.1 for each application. So that means the population of those germs based on each application is equal to that. Write an equation. We did. Suppose your kitchen continent has 10,000 germs. Okay, so instead of 100%, we have to put 10 to the 10 germs. So we're going to say it starts off with this population. How many applications were required to eliminate all the germs? Well, that's a trick question, because any decay graph will never reach 0. There's nothing I can put here as an exponent that will result in this as in 0. We can get very close, but we'll never get rid of all of them. So that was a trick question, because a reduction of a percentage, there's an old Greek myth. You're in a town here, you're traveling to this town, and each day you travel half the distance that's left. So the first day you travel half the distance. Then you travel half the distance that's left. And the next day you travel half the distance. The next day you travel half the distance. Next day you travel half the distance and half the distance and half the distance and half the distance. And you're never, and look at this, this is suddenly looks like a growth curve, but you're never reaching the town. I just have to pause for a second and knock at the door. But let's say we want to reduce the germs significantly. Well, we know that 0.1 is going to reduce this by two decimals each time. And when I square it, it'll be 4 decimals. There are 10 zeros here. So if I do this about at least 10 times, I would actually only need about 5 times. I will reduce this 10 million bacterial population to about 1. So if I put this to the exponent of, let's say, 6. So I spray the bottle 6 times, and I multiply it times my billion population. Suddenly I have 0.01 bacteria. So I only had to spray this bottle 6 times to get it down to less than 1 germ. But I can never bring it down to absolute 0. Now, if you consider anything less than 1 dead, then we could do this. When will this formula be equal to 1? Because any application beyond that will kill the last germ, right? So we just start by dividing both sides by this. And when I do this, I get into a weird decimal. So 1 divided by 10 to the power of 10. And get into this long decimal like this. So essentially, when will this be equal to this? Well, I could do the long plug in the calculation, but I'm going to take a log of both sides, and I end up with this. It's going to be equal to the log of this divided by the log of that. So I'm going to take this log, and I'm going to divide it by 0.01 log, and I get 5 applications. Like my guess of 6 was good. So that means when I spray it 5 times, the population of these germs will be equal to 1. So clearly, if I spray it 6 times, I pretty much destroy that last germ. So technically, you will never destroy all germs, but if we're going to look at it this way, as anything less than 1 is a destroyed population, then 6 applications will destroy the last germ. So I got lucky on the guess. And 15 and 16, there's a lot of questions in this chapter, and they're all pretty much the same. So we got a town whose population goes up, looks like. 15 years later, its population grew to 1250. Determine the average. So they want to know the percentage. So this is an interesting thing. What was the initial population? 8,400. And it's going to be multiplying by some percentage. That's 1 plus some percentage. And it's going to go to the power of t. Well, in this case, they tell me the population finishes here. So I know that my finishing, so this is, this formula here is equal to whatever population I want to find out based on time is equal to this. Well, they give me the population I want to find out. They tell me the initial. They don't tell me the percentage, but they tell me the number of years this happens at. This is actually solvable. So let's call this 1 plus x percent. So now we just need to figure out what x percent is. Well, we go in reverse bed mass. So our first thing to do is divide by this on both sides, and it disappears. So 12,500. And an easier way to look at this is you can always just cross off these zeros. Right, this and this. And it's 125 divided by 84 if you want to save time on a test. And I get this. Try to keep as much as that. I'm going to even put it in memory. As much of that as possible. And it's equal to 1 plus x to the power of 15. Well, I can take a square root of 15 at both sides. And what a square root of 15 on your calculator, you're going to see this. It says x to the y. So you first punch in this number, then you press this symbol, and your y here will be 15. So I'm essentially going to take a square root of 15 or a 15 root of both sides. On this side it cancels out. So on this side I have to take a 15 root of that number. Well, I already have that number in my calculator. So I'm going to press my x to the y button. It's sometimes on the second function. There it is. And now I'm going to put 15 and hit equals. And I get this number. So that means this, and we'll just round it up somewhere right there, is equal to 1 plus x. When I subtract x from both sides, or 1 from both sides, I get this. X must be equal to that. And what is that as a percentage? That is 2.67%. So that means the rate of change of this town, if it grew from 8,400 to 12,500, is 2.67%. So not too bad. All right, on to the next one. These questions are, you can actually figure it out because they give you the exponent. The other ones are tougher because you don't know logs yet. So this thing is growing, this yeast is growing every 3 hours by 75%. And this is a tough one because it's every 3 hours, not every hour. At 9 a.m. there are this many. So we have an initial population of 200. It's growing 75%. Okay, well, that means our initial population times 100 plus our growth rate. And normally it would be to the power of t. But to the power of t is every hour. So we actually have to do this. So that if I put a 3 in there for t, 3 divided by 3 is 1. And that will increase my percentage at that time because it's every 3 hours. And it starts at 9 a.m. So 9 a.m. is considered 0 hours. Replacing the information I have My initial population here is 200. So I have to can replace that. This 100 plus 75 is the same as 175%, or 1.75. That makes sense. That's a growth curve. Write an equation that models after 9 a.m. Well, okay. The population of my yeast cells, based on my time in hours, is going to be equal to this. And yeah, it's not all quite on the same level. I can bring this down a bit, and I can bring this in a bit. Something like that. And technically, it'd be smarter to put this inside here so I don't accidentally confuse the numbers. Explain each part of your equation is related to the thing. Okay, well, here's the initial population of the cells. That's the growth rate of 75%. I've got to include the 100%. If it was decaying by 75%, it would be 100% minus 75%, which would be 0.25. But it's not. It's growing. And then this t divided by 3 is because every 3 hours instead of every hour, it will double. Or in this case, 1.75. So that means I have to account for every 3 hours by putting this divider. And you can test this out by throwing in 3 and then 6 and then 9. This fraction when it's 3 will become 1. Well, this fraction when time is 6 will become 2, which is what you want. This fraction when this t is 9 will become, this exponent rather, will become 3. And that's what you want. You want your exponent to go up 1 unit every 3 hours. So you have to divide by 3. Well, that was easier because they didn't ask us to do any calculations. And then they've got these extending questions, which are always difficult. I never really do them, but I'll give them a shot. And if I get snagged here, it's your fault. Here we go. Always read, in the year 2002, a single baby girl born in Alberta was given the name Nevea. 2 years later, there were 18 girls, including the first one with that name. By year 2005, there were 70 girls. So we should look and notice that this is 2 years, and 2005 is 3 years. 70 girls with that name. Investigate whether or not this is an example of exponential growth. Okay, the best way to do that is to do it as a T cell. And you're going to put your years here. So at year 0, there was 1 girl. So that's the number of girls. And then it says 2 years later, so we don't have any data for 1. But we do have 2 years later, there were 18 girls. And then 3 years later, there were 70 girls. So we might not have enough data. However, I can see that the jump here from 1 to whatever this is was significant, and 1 to here is significant, and 1 to here is significant. We might even be able to guess what this first year happened. But if I look at this, this jumps up 52. And there's no way this can jump up more than like 18. And it's probably something like 15, which means this is like a 3. So it's a 2. So the best way to come up with a ratio is to take 70 and divide it by 18 and see if that will work. So 70 divided by 18 is equal to this, and if I 3.888. So really we're talking about something that is growing by a ratio of 3.88 for each year. And the initial baby is 1. So we're going to see if this formula works. Number of names based on year is equal to 1 times 3.88 to the power of t. Let's see if we can figure out how many babies there were after year 1. In year 1, there should be 3.88 babies with that name, or roughly 4. So really, we should probably use 4. My guess is we're going to use 4, because you won't want a round baby, but we use that. And if I look and put this as year 2, I should get an 18 out of it. So 3.888 to the power of 2 times 1. 15 babies instead of 18. And then finally, where it gets more accurate is 3.888 to the power of 3 times 1. I get 58. So if I'm going to guess now, instead of 3.88, I'm going to make that 4. I'm going to make it 4. So I'm going to make it 4 to the power of t. And this is going to be the formula right there. And I can say that that's essentially a 400% increase. And so now if I guess, that's going to be 4. And if I put 2, 4 times 16, pretty close. If I put 3, 64 times 1, it's pretty close. So it might even be 5. 5 squared would be 25. So it's somewhere about 4 and 5. It looks like it. Determine that the growth rate might be and create a possible equation to the model of the growth as populator name. So really, you're going to get more information down here because of we're not sure what's going on here. Would it be a 1 multiplier? It looks like it's more than a 1 multiplier. So if I assume 4 to the 2 is 16, what's missing? Well, there's a plus 2, right? Or there's a multiplier and then a subtraction to get a more accurate number. So what I would actually do is I would make a huge assumption and say I can't have a weird number here. And I'm going to say something like 4. And I'm going to use this equation. I'm going to say, okay, my number of girls is going to be based on a number here, an initial number here, times a ratio that I'm going to use 4. And it's going to be just a normal thing here. And it's going to be plus or minus a mysterious value here. And if I look at my first girl, I get number is this is equal to I, and it's going to be 4 to the 0, which is just 1. So I get I plus B. So that means the initial value, or B, is equal to, it's called the initial value is equal to 1 minus B. Now, if I look at the second year, in year 1, I have 4 babies. 4 babies is equal to my initial, and it's 4 to the 1, so I get 4, plus B. But I just figured out up here that I is equal to 1 minus B. So if I multiply this out, I get 4 is equal to 4 minus 4B plus B, so it's minus 3B. And minus 3b is equal to 0, and it looks like that. Well, let's keep going, because the only accurate number I really have is the 18. So I'm going to do 18 is equal to I, which I don't know, but it's 4 to the power of 2, which is 16, plus a mysterious b. Well, I do know I up above is 1 minus b, and it's going to be equal to 16 plus b. So that's 16 minus 16b plus b, which is minus 15b. So that means 15 is equal to 2 minus 15b is equal to 2. And which means that b is equal to negative 2 over 15, which is roughly negative 1 over 7.5. 0.5. Now I have a more accurate equation, and I go back up here and put the minus, and I put the minus 2.5 in the original equation up here, which is this one, to figure out my I. Well, 1 minus 2 over 15 is actually 1 plus 2 over 15. So I is equal to 1 plus 2 over 15, which is 17 over 15, which really my equation is going to be, therefore, my number of girl names. Well, I got to keep it all, actually. We'll just put this to the side for now. My number of girl names is equal to, what was my initial? 17 over 15 times 4, and it's not quite accurate. Oh, no, it is. To the power of t minus 2 over 15. If I put in 0 here for year 1, this becomes 1. And I get 17 over 15 minus 2 over 15, which is 15 over 15, which is 1. If I put in 2 here, I get 16. Or sorry, 1 here, I get 4 times 17 over 15 minus 2 over 15. I get 4.4 girls. If I put in a 2 there, I get 16 times 17 over 15 minus 2 over 15. And I get my 18 girls. Now, the big trick is if 17 will work. So 17 is year 3. So it's 4 to the exponent of 3 times 17 over 15 minus 2 over 15. 72.04. So it's pretty accurate. It's losing accuracy on this number, and actually these numbers should be more accurate. So I probably should have used this number to come up with a more accurate equation. And I could have. And actually I should have used these last two because they're going to be more accurate. But this is essentially the equation. Right? And it's assuming a growth of 4. That's the problem. Is I don't have enough. I need more data. Possible equation. Discuss any limitations to your model. Not enough data. I really need more data in the big numbers to get an accurate idea of what the growth rate is. And that will really finite these terms here. Yeah, not bad. There we go. Psychologists have performed experiments in which you had people memorize lists of words and then tested their memory. So the bummer here is it's really hard to see if that's a growth or a decay until we break it down. And this is really, with given time, it's clear that we're going to forget it. But let's break this down into something we can understand. Okay. If I look at the top, it's just a multiplier. It's 100. And what is it multiplying? It's multiplying this. 1 over this. So it's clear that we're talking about a percentage of 100 multiplying something. The question is, does that go down or does that go up? Well, it's clear that as this denominator goes up, the whole result goes down. So the 100 is going to get smaller. So we're talking about a decay. But if we want to write it in terms that make sense, we can put this whole bracket up top like this, and we can put it to the minus 1. That's all it means. Now, it's very hard for me to add those because with this t here, it's clearly multiplying this t, and this exponent is applying to this t only. However, you can, what would be a good way to do it? We can it's clear that that's plus 1 is being added to it, right, in the denominator. And we're not allowed to distribute this negative 1 to individual things. You have to add them first, and they can only be added if we have the same base. What would be a better way of expressing this? I guess we should just use this. It just wants us to graph the thing with technology. It's going to be a decay, though. So we're going to write it both in my way and in their way. We might as well just answer the question. So R of t is equal to 100 divided by 1 plus 1.71, was it? 1.08. Oh, and it's a very specific. Times t to the exponent. Oh, I didn't notice that exponent was a specific exponent. So this is not going to be a decay curve, I don't think. Okay, and we can replace that with t. And let's see. First of all, yeah, you should always figure out what it's going to be at time 0. It should be 100%. Yeah. Because this becomes, at time 0, 0 to the exponent, this all becomes 0. So you get 100 divided by 1. And it's clear that it looks like a decay curve because the memories of your words are going down. But it's actually not really a decay curve because this exponent is not changing. Just this base of time as an exponent is changing. It's more like an inverted, limited parabola than a decay curve. For it to be a decay curve, this t value would have to be up here. But we can see as t goes up, this whole value goes up, making this whole denominator going up, which makes the overall value go down. But it's technically not a decay curve. Predict the percent of words remembered after 24 hours. So that would just be R of 24. And we will only remember 32% of the words at R24. And you'd be able to find it right here. Y is equal to 32. Roughly 25 hours. 30.205. Roughly 24 hours is where we would remember 32% of the words. And you can see like 100 hours later, you're still going to remember 26% of the words. And interestingly enough, many hours later, like 800 hours, you're still going to remember 18% of the words. But I don't. This does not count as a decay. It looks like a decay, but it's not.